our next demo is about PyCPL and PyEsoRex, the ESO Common Pipeline Library in Python. It's by Anthony Horton and team. So now I invite team to share screen.
Hello, good morning, good afternoon, or good evening. I'm Anthony Horton from AAO at Macquarie University, and I'm here to talk about the CPL project. So before I dive into demonstrations, I'd just like to start with a bit of background. So firstly, for those who aren't familiar with it, what is CPL? So just quoting from the CPL webpage, the CPL is the Common Pipeline Library, comprising a set of ESO C libraries that provide a comprehensive, efficient, and robust software toolkit to develop astronomical data reduction tasks known as recipes. These data reduction tasks can then be executed manually by a user, or can be triggered in an automated data reduction framework known as pipelines, which are used at ESO to monitor the health status of VLT instruments for quick look data processing at the observatory and the creation of data products available from the ESO archive facility. So basically, CPL is the fundamental tool for building data reduction pipelines for ESO VLT instruments, and that has been the case since 2003 when CPL was released, and it's going to continue to be the basis for the ELT instrument pipelines. So these data reduction pipelines are built from recipes, which take the form of compiled shared object libraries, the .so files. And so each recipe performs one step in the data processing, or one task in the data processing. So it takes a list of input files, performs the task on them, and produces a set of output files. And then each recipe will have a set of parameters associated with it that are used to control the processing. And then you can produce a pipeline by daisy chaining these recipes together. So this is supported by the functionality from the CPL library. So as well as the framework for creating recipes, you also have data types for representing images, masks, tables, matrices, property lists, and so on. There's a host of statistics, arithmetic and conversion operations for those data types. There are some higher level tools, for example, world coordinate system support, geometric transformations, wavelength calibration, and so on. There are tools for managing FITS files and other data access tools. There are some methods for integrating those data products into the ESO data flow system. And CPL also provides the basis for ESO's HDRL, the high-level algorithmic library that has more complex data reduction algorithms in it. At present, there are three existing tools for running these recipes. The first is Reflex, which is a graphical environment for running data reduction pipelines to reduce your data. There's Gasgano, which is primarily a graphical data file organization tool, but that also supports running these CPL recipes on the data. And finally, there is ESORex, which is a command line utility for running CPL recipes. So briefly then, what is CPL? Well, PyCPL, sorry. CPL was developed in C for the usual reasons of efficiency and speed of execution, and it's well tested and understood. However, with the increasing popularity of Python for data reduction in astronomy, there's a need to provide access to CPL from a Python environment. And PyCPL is intended to do this in two ways. So the first is by making it possible to run existing CPL recipes, those that are written in C, from Python, and to access the results from Python as well. And secondly, to create new recipes directly in Python, making use of the functionality provided by the Common Pipeline Library. So when you take those together, then it becomes possible to develop a new pipeline in Python and to have those pipelines seamlessly combine existing CPL recipes with new Python recipes that leverage functionality from CPL, but also other scientific Python libraries such as NumPy, SciPy, AstroPy, Pandas, Matplotlib, etc. So interoperability is important there. One part of PyCPL is PyEsoRex, which is a new recipe execution tool that has both a command line interface intended as a replacement for ESORex, does the same things, but it also, there's an object-oriented Python API that you can use from Python code or interactive Python sessions. And this tool can then run both classic CPL C recipes and PyCPL Python recipes. And then there's PyCPL library itself. So we have wrapped the CPL library with an idiomatic object-oriented Python interface. And we also have templates for producing Python recipes, which takes the form of a recipe base class. Just a couple of quick caveats about the demo today. PyCPL is currently in pre-beta. We're due to release a closed beta next week. So any details here are subject to change for general release. And also ESO standards currently require pipelines for ESO instruments to be implemented in CPL. So that's the way things are for now. However, PyCPL will soon be available as a way to rapidly prototype those pipelines in Python, as well as developing pipelines for other purposes. So I'll start with just quickly showing you the command line interface. So if any of you are familiar with ESORex, you'll find this looks very familiar. So this is ESORex, just displaying its various command line options. It's a very traditional command line tool. And PyEsoRex is essentially the same. It's still in beta, so we don't have all of the options there, but it's exactly mirroring ESORex, existing ESORex functionality. And so, just as a very quick example, we can run PyEsoRex, optionally providing it a config file, providing the name of a recipe. This one is from the VLT instrument giraffes data direction pipeline. It generates master bias files, and we have to give it a soft file, and the soft file is just a list of input fits files, and we can then run this recipe and we get some console output. It also generates log files and tells us that it combined 5 bias images and produced a master bias image. But I don't want to spend too much time on the command line interface. I'd like to move on to the Python interface. And so I have a notebook here that shows how this could be done in a interactive Python session, but of course you could equally do this in non-interactive Python code. So the process, you just have a few other imports to begin with, but you start by importing the PyEsoRex class and then creating an instance of the class. So by default, when you create one of these, it will look for a config file in a default location. So there's a .PyEsoRex directory in your home directory. It looks for a PyEsoRex.rc file. And from that, in this case, it found one. If it doesn't, it will just use its default values. And you can then print the parameters that it gets from that config, this parameters property. And see here's a full list of parameters, including things like the recipe directory, where it looks for recipes and some logging settings and so on. Alternatively, you can create a PyEsoRex instance by specifying a config file at the start. And so in this case, I have a slightly different set of parameters. This includes a different recipe directory. You can also write config files. So this will either write the existing settings to a file, or with a optional argument, it'll write all the default settings to a new file. And you can read them as well. So having got your PyEsoRex instance and it's configured to your liking, you need to load a recipe. Well, first you can list the available recipes. So let's have two methods. One is intended for a machine readable dictionary with a bunch of metadata. And there's also a more human-friendly text listing. It just lists here, these are the names of the recipes. These are all from the Giraffe instruments pipeline. And there's a synopsis here, just a short description of what they do. You then have to load it. There's a load recipe method. And then once you've loaded it, you can then look at the recipe parameters. So there's a, here, this recipe, the master dark recipe has quite a few of these. They can be various types. So some of these are options. They're basically enums, parameter enums. Others are just numeric values or string values. And you can also load recipes just by assigning to this, this recipe property. So I've loaded another one here. This is the Giraffe master bias recipe. And you see it has a different set of parameters. And these can be changed. So because this recipe parameters property has an update method, and you can just pass in a Python dictionary of key value pairs, name value pairs, and then you can see this has changed the stacking method to median and set this bad pixel mass creation flag to false. Now the recipes can also use configuration files of their own. So we have a corresponding set of methods for writing and reading recipe configuration files. And these are all compatible with the ones used by ESORex. So if you have ESORex configuration files for recipes, you can use those in PyEsoRex. Having set up the recipe, then the next step is the soft file, and this is the file that has the details of the input fits files. So I have one here, which I can open. Not very interesting, it's just here. This is a very simple one. It's just a list of paths to fits files and then a tag. And this tag is marking all of these input files as bias streams. So then we can run the recipe and we get an output very similar to the command line. But having done that, we get a result returned. That result is a PyCPL object. It's a frame set, which contains frames. And each frame, in turn, has the details of an output fits file, along with some metadata for it. So we can have a look at that. So, for example, the first frame here has this path. It's tagged as a master bias. It's tagged as a data product rather than a raw or calibration file. It's tagged as final, and it's tagged as having the type image. Now, these frame objects, we have a method to open these as open the corresponding fits file directly as an AstroPy HTU list. So you can just straight away have a look at that. We've just got a single HTU in this list, primary HTU, and then we can quickly look at the header or the data as a NumPy array. Or alternatively, we can open the fits file as a AstroPy NDD data, CCD data object. More or less the same thing. And there it is. And we can then use bat.lib or whatever to take a quick look. And there's our master bias file. So that's running classic CPL recipes in C. So PyEsoRex, of course, can also run recipes that are written in Python. So the process is almost exactly the same. We create a PyEsoRex instance. In this case, I've used a different config file, and this one has two recipe directories in the config. This first one is where the giraffe pipeline recipes are, and this second file is a local file here, local directory here that has a couple of Python files in it containing some example recipes. So now, if we list the available recipes again, we have 3 additional recipes at the bottom, and these are Python recipes, but they're treated exactly the same as the classic CPL recipes as far as PyEsoRex is concerned. So then we can load one, and this is a very simple hello world example called hello fits. And we can give it a soft file. We'll just use the same one again that has the giraffe bias frames in it, and we can run it. And this toy recipe just says hello to each of the fits files. So let's just have a look at how that's actually done from the recipe. So this is the Python file that contains the first 2 recipe examples. And here is the recipe we just run. It's a class. It derives from this PyRecipe base class. The first thing here, we have a set of class variables that have to be set. This is the metadata for the recipe. So name, author, copyright info, description, contact email, synopsis, and a version number. And the only other thing that's essential is to implement the run method. So this takes 2 arguments, a frame set, so that's the set of input files, well, the details of the input files, and settings, which is a Python dictionary of settings to apply to the recipe's parameters. In this case, this is a simple recipe, has no parameters, so we just ignore that, and we're just printing a greeting to each of the input files. And generally speaking, your recipes will have parameters instead. So I have a slightly more complex example here. Hello user, and when we load that one and print the recipe parameters property, we get this list here. So we see there's a username, an endfits, and a reaction parameter. Now, if we look at the code, we can see how this is actually implemented on the Python side, of the recipe side. Again, we have these this metadata that we have to set. We have a run method, and in this case, we also override the init method, and here we create a self parameters attribute, which is a parameter list. This is one of the classes from PyCPL. It is just a simple container for parameters. And then we have 3 different parameter classes here that we create. So there's a parameter value, which is a simple value. And we have to set a name, context. In this case, that's just the name of the recipe, a description, and a default value. And the default value is also used to set the data type. So in this case, this is a string parameter. We also have a parameter range. Now this is like the value, except that it can only can be set to values in between a minimum and a maximum. This one is a integer parameter with a min of 1 and a max of 5, and a default of 30. And then finally, we have the enum parameters, parameter enum class, and these have a fixed set of possible values. Again, this is a string parameter with 2 possible values. And then we have a row method. This one does actually pass the settings as they come in. So it just iterates through trying to match keys from the dictionary to the names of parameters and setting the value. And then it prints some messages. So go back to the notebook and see what we get. So we get, again, it's a simple hello world type thing. Hello unknown user, nice to see you. And then a listing of the first 3 FITS file paths. And just like the CPL recipes, we can change some recipe parameters and then run the recipe again. It's slightly more personalized greeting. And we can write or read recipe config files, which have exactly the same format as the classic CPL recipes. Okay. So those are some toy examples. I'll dive a little bit more into PyCPL. So what is in PyCPL? Well, everything that's in CPL. So PyCPL is a wrapper around CPL. So all of the functionality that's in there is being bound to the Python API. Mostly in a very similar fashion, though in places we adjust the interface to make it more Pythonic. And there are 4 submodules to the library. So the first is core, and that's the one that has the classes for all the basic data types. So we have an image, mask, table, vector, bivector, matrix, and property classes. And those are all pretty rich classes. Things like image in particular have a lot of methods for doing arithmetic and logical operations and statistics and so on. We have some containers for these data types. So we have image list and property list. We have logging and console message system via this message class. We have error handling. So we have a set of custom Python exceptions, and errors generated from the CPL C code are translated into Python exceptions so they can be handled in the normal way. I'll show an example of that very soon. There's some statistics functions, and there's a polynomial class. The next module is TFS. That's for the ESO data flow system. So these are functions to ensure that the data products are compliant with ESO DFS standards. So you have things there that check the metadata and sign it with MD5 checksums and so on. Then we have the data reduction system, which has a few functions like simple object detection and aperture operations, detector characterization, fast Fourier transforms, some image alignment and stacking tools, nonlinear fitting, and WCS. And then finally, we have the UI module, which is, this is the framework for building the recipes. So this is where we have recipe classes, C recipe and by recipe, frame and frame set for FITS file management, and the parameter classes, and a few more exceptions. So just to show you a slightly more substantial example, again, creating a PyEsoRex instance and setting an example file. This one is a little different. And just to show an example of a frame set being used here, we can just load that soft file and get the data. This is 3 raw object frames, a master dark file and a master flat file. And just showing some of the interoperability here, we can load that image, load one of these raw frames as a PyCPL image, and then we can pass that directly to matplotlib for display, because an image can be used in places where numpy arrays are expected. And so we can see a raw image here with a lot of hot pixels. can load our example recipe, which has a look at the description, run the recipe, which then processes our 3 raw files. It does a simple dark subtraction and flat fielding, and look at the results. We have a frame set with 3 frames in it, and we get the pass to all those files. They're tagged as objects, they're tagged as data products, they're tagged as intermediate level and image type. And then we can have a look, again, just using the image class from PyCPL to load one of these files, and we get a nice picture of the galaxy. Then finally, just a quick demonstration of how the error handling is working. So this Python recipe, if you give it an inappropriate set of input files, in this case, give it just these bias frames, it can throw a PyCPL exception. So we have a custom exception for data not found, and this is all very familiar to Python. The interesting thing is that the same thing happens when errors are generated from the CPL code. So if one of the CPL functions generates an error code, it's translated to a Python exception. So here's an example where we try to create a mask object with a negative dimension, and the CPL error that's generated in the C code gets turned into a PyCPL illegal input error exception. And these being Python exceptions, you can do all the usual things. You can catch them, you can handle them, you can re-raise them. So here we catch that exception, print an error message using the messaging and logging system, and then re-raise the error. So that's it for what I want to show in the demonstration. If you'd like to know more, then there is a poster in room 1 on PyCPL using PyBind to bring Adapt-C libraries to Python. So there's a bit more technical detail there and a discussion of some of the challenges of implementing this. Please do ask any members of the team any questions you do have. So I'll do my best to answer any questions on Discord or GatherTown for the rest of the week, depending on what you would like to ask. So maybe ask somebody else in the team. So you can ask me about PyEsoRex or the Python API. Those are the areas that I've been most involved with. Or Anthony Heng about PyBind 11 and the C++ layer, which I didn't even really mention. Issues of memory management and error handling and so on. Nora Llorente about how we've managed this and scheduled it. Or Ralph Balzer or Lars London about the underlying CPL library or where this is all going. And just a reminder, I had a note on this at the start. These notebooks are on GitHub at this address if you would like to look at them a little bit more carefully. That's along with the example code as well. And I'll finish there. Thank you.
Okay, thanks a lot for a very informative demo of PyCPL. And now we have time for a couple of questions before we go for a break. And there are a couple of questions written in Discord channel. So I will take one for time being. What should C recipe writers already do now in order to make a potential shift to Python recipes in future easy?
Okay, that's an interesting question, because yes, the way that it's all been set up, probably very little, because PyCPL can run recipes written in C just exactly the same as it does in Python. So if you're writing C recipes now, you can use them in PyCPL as they are.
Okay, thank you. There there is another, I want to take it. The inclusion of DRS class in PyCPL means that it includes also SDRL tools, though it is already answered. So can you add statements on that?
Noria says it there, indeed, yes. So we have not included any of HDRL in this, but yes, indeed, there are plans to do that as the logical next step once PyCPL has been done.
Okay, thank you, perfect. So do we have any other question here? No, I don't see any. I mean, these discussions are already being clarified by the team. So thanks a lot, and thanks a lot to all the speakers of this morning session.